Welcome, ladies and gentlemen. Let's go ahead and think about what trig function, sine, cosine, or tangent, relates my given angle, 67 degrees, my unknown side length x, and the 53 inches. What trig function did you use, sine, cosine, or tangent, for that first one, number one? Mark? Cosine, raise your hand if you chose cosine for that one. Cosine? In relation to 67, Mark, what side length is x? Opposite, adjacent, or hypotenuse?
It'd be sine.
Sine. Raise your hand if you chose sine for number one. Sine function. Great, thank you. Let's go ahead and write an equation then. Sine of an angle equals a fraction. All right, because sine is a ratio. What angle? In this case, 67 degrees. What's my fraction? Well, that's opposite over hypotenuse. And so in relation to 67 degrees, x is the side length that's opposite it. And hypotenuse is always opposite the right angle, so that's 53 inches. Raise your hand if you have this equation. Sine of 67 degrees equals x over 53. Excellent. Now we can go ahead and solve for x. Depending upon where x is, we'll use a different series of inverse operations. It looks like for this one, it's a one-stepper. We can undo that division by 53 and solve for x in one step. Solve times 53 times 53 and get my exact answer. X equals exactly 53 sine of 67 degrees. I don't know what that is, though, so I'm going to go to the calculator and get an approximation. So on my calculator, I'll go ahead and make sure that I'm in the proper mode. For us, we had 67 degrees, so I'm going to make sure that I'm in degree mode, and I am. Now on my home screen, I can simply enter 53 times the sine of 67 degrees, close input, and that's about 48.79. Raise your hand if you had about 48.79. 48.79. Way to go, you guys. That's awesome. Great work. What would a label on that 48.79 be? What would a label on that 48.79 be? Will? Inches. I'm down, so we'll go ahead and include that as well. I can scooch. All right. What questions do you guys have on number one? That I made space that I forgot about. And number two, what trig function relates 40 degrees, 15 feet, and x, my unknown side length? Go ahead and share with the class when I call on you. So what trig function did you guys use for number two? Taylor? Cosine. Raise your hand if you use cosine for number two. Cosine? Awesome. So our equation is cosine of an angle equals a fraction. In this case, cosine of 40 degrees equals our ratio. Our ratio for cosine is adjacent over hypotenuse. So adjacent to 40 degrees is 15 feet. Remember, adjacent is adjoining, next to, touching, but not the hypotenuse, so that's 15 feet. Over the hypotenuse, in this case, is x. Depending upon the location of my variable, we'll use different inverse operations to solve for it. Here I'm in the denominator of a fraction. That's okay. I know how to get that out of the basement. What are you going to do to both sides to get that variable out of the basement? Rachel?
Multiply both sides by that.
Good, thank you. So we can multiply both sides by that variable expression, and then I'll get it up on the ground floor. X times cosine of 40 degrees is equal to 15. And now we can solve by division. So all we have to do now is undo that multiplication. We can undo multiplication with division, and we'll get our variable alone. So it looks like x is exactly 15 divided by cosine of 40 degrees. However, I don't know what that is, so I'm going to get an approximation by using the calculator, and I'll get 15 divided by cosine of 40 degrees, close angle input. And it looks like we get about 19.58. Raise your hand if you had about 19.58. Good, and you're going to share the label with me here in just a second. So that's about. And what's our label on this one going to be for number two? Emily?
Feet.
Feet? Awesome. Thank you. And always striving for PDF full. Comma, baby. And one to go. In this last one, right? In this last one, what trig function relates angle x, 17 centimeters and 43 centimeters. Go ahead and share with the class my calling you. So what trig function relates x? 17 centimeters and 43 centimeters this time? Carson? Cosine? So raise your hand and use cosine for number 3. Cosine? No, not cosine? Oh, so what side length, right, in relation to x is 17 opposite, adjacent, or hypotenuse? Opposite is 43, opposite, adjacent, or hypotenuse? Adjacent. So which trig function is opposite over adjacent? Tangent, absolutely. Raise your hand if you use tangent. Good, thank you. So tangent of an angle is a ratio. Tangent of an angle is a ratio. In this case, my angle is x. My ratio is opposite over adjacent. So for us, that's 17 over 43. Great. So now we get the inverse involved like Carson was talking about. In order to find a missing angle, that's when we get to use our inverse trig function. What undoes the tangent function so I can solve for my unknown x that's hiding inside the angle? Well, inverse tangent undoes tangent. And so we're basically taking the inverse tangent of both sides. We're choosing the inverse tangent, right, of function because that undoes tangent and gets my variable input alone. So I'm trying to solve for that squiggle underline x, right? So what's the inverse tangent of x? That's just x. I've gotten my variable alone, and it's given by exactly the inverse tangent of 17/43. I don't know what that is, but I'm going to see. That's about second tangent is inverse tangent of my ratio is 17/43. Close input. Voila! About 21.57 degrees because we're in degree mode. Raise your hand if you had about 21.57 degrees. You already had that? Hey, that's great. So inverse trig functions undo, right? Undo trig functions to get unknown angles versus using your regular sine, cosine, and tangent buttons are to find missing side lengths. Great. So let's go ahead and PDF. I'll hold this. So what do we have 21.571. Awesome. What questions do you guys have on the Bellwork today then? Okay, I'm going to go ahead and pause the recording and we'll do our homework check now. Ladies and gentlemen, today we're going to step out of our comfort zone, right? We're all comfortable having a right angle in our triangles because then we can utilize all our right triangle trigonometry from last year in geometry. We've got our Sohcahtoa, we've got Pythagorean theorem. What happens if we don't have a right angle? And that's going to be the investigation for today. We're going to have two new tools, the law of sines and the law of cosines. That are going to be our ticket to success when we're trying to find missing sides or missing angles in a triangle that doesn't have a right angle. So we're going to check that out today. We're also going to do some real world applications with it in the next 2 days. One of the most important applications of trigonometry is to find unknown lengths or angles in triangles. In the last lesson we reviewed how to find side lengths and angles for any right triangle, right, where we had the 90-degree angle. Today we're going to extend our knowledge to be able to find side lengths and angles for any triangle. A right angle will not be necessary. So let me give you an idea of what we'll be able to do. Let's take an arbitrarily drawn triangle ABC that doesn't have a right angle. So I purposely made this picture so that there's no right angle in this triangle. Now let's go ahead and draw an altitude h from angle B. So everybody, let's go ahead and drop altitude h from vertex B directly down so that it hits the side length opposite it at a right angle. So let's go, everybody draw altitude h, and that should be perpendicular to side length AC. And I'll go ahead and label that h. Is everybody drawing your altitude h? Awesome. All right, let's go ahead and state ratios now for the sine of angle C. So let's go ahead and find angle C, and we'll jump inside the right triangle that we created. The sine of angle C I'll go ahead and do in blue. And we can see the sine of angle C by just focusing on that left-right triangle. Everybody see it? the left-right triangle would have a sine ratio opposite over hypotenuse. That would be what ratio? Well, it would be opposite angle C would be side length what? H. And the hypotenuse in that left-right triangle would be what, Jacques? A. So guess what? The sine of angle C is H over A. Good. Let's go ahead and focus now on this right side, little right triangle, and state the sine ratio for angle A. I'll do that in green. So the sine of angle A is a ratio, opposite side length over hypotenuse side length. It's just that my little triangle right here has opposite side length H over hypotenuse C, and so sine of angle A is H over C, and I'll write that in green. All right, now each of these two equations, sine of C and sine of A, they have H in common. They have that variable H in common. So let's go ahead and solve each of those for H. In my first one, H would equal A times sine of angle C. In the second one, H would equal, if I multiply that C over, C times sine of angle A. And if H equals blah and H equals blue, then we have no choice but for blah to equal blue. What? Well, if H equals the sine, A times sine of C, and H also equals C times sine of A, we could rewrite that as A times the sine of angle C is equal to the other H, which is C times the sine of angle A. Why all the fuss? Well, because now we can rearrange these, right, we can rearrange this into a proportion that will be known as the law of sines that we can use to find missing side lengths and missing angles anytime we have an opposite side angle pair known in a triangle. What? Let's go ahead and rearrange this by dividing. We're going to divide both sides by A, divide both sides by C, and we'll get the sine of angle C over C is equivalent to the sine of angle A over side length A. There's nothing special about angle C and side length C. We could have done the same thing with angle B and side length B. What's important is that this ratio holds true regardless of what opposite side angle pairing we're referring to. Let's take a look at our law of sines in general. So the law of sines holds true for any triangle ABC. The sine of angle A is to side length A, just like the sine of angle B is to side length B. That's also equivalent to the sine of angle C over the side length C. If we prefer, we can put unknown sides on top. A is to the sine of angle A, just like side length B is to the sine of angle B, bless you, just like side length C is to the sine of angle C. So we only use two ratios at a time, right? By writing a proportion, we'll focus in on opposite side angle pairs. If we can complete given information with one opposite side angle pair, that is, we can fill in one of these fractions entirely, then we'll be able to use law of sines to find missing side lengths and angles. All right, so let's go ahead and consider what information might be given in order to use the theorem. And this is like a reading question. Well, we need to be able to fill up one of these fractions. So we either need both side length A and angle A, or side length B and angle B, or side length C and angle C. We need to know one, right, opposite side angle pair completely. So if we know both C's, then we're good to go. If we know both A's, then we're good to go. If we know both B's, then we're good to go. So in general, we need one opposite side angle pair entirely. So we need to know one opposite side angle pair entirely, and then we're able to use the law of sines. So we need to know one opposite side angle pair, either both A's, both B's, or both C's, and then we're ready to go. Ready to go where? Well, let's see how we might use the law of sines to find missing side lengths or angles. So let's take a look. In this first triangle, we're given information about angle C, that's 34 degrees. Angle B is 85 degrees, and side length C is 3.9 inches. Let's go ahead and fill in our given information and see if we can't find side length B. So let's go ahead and fill in our given information. It looks like angle C measures 34 degrees, so we'll put this here. Angle B is 85 degrees, so we'll put that here. And side length C is 3.9 inches. Go ahead and survey your triangle. Do we know one opposite side angle pairing completely, that is both A's, both B's, or both C's? Joe?
Yeah.
Which we know?
C.
We know both C's, right? We know both C's. We know angle C is 34 degrees, and we know side length C is 3.9 inches, so we have a complete opposite side angle pairing. We know both C's, so we can use law of sines. Let's see how. If we want to find angle B, I can use any of these forms. I like to focus in on the one that has my unknown, in this case, a side length, little b, on top. And so which of these forms would I like to start with? I'd like to start with b over sine of b. That way my unknown's on top and I'll have less steps to solve for. Keep in mind I can set that to either of these other two ratios. Depending upon which information I have, I'll choose to use the one with a's or the one with c's. Let's go ahead and take a look. Joe told us we know both c's, and so I know I'm going to start out with b is to sine of angle b, just like side length c is to sine of angle c. If we choose to start with the law of sines that has side length little b on top, then we better make sure we have side length, right, little a or little c on top of the other one. So we always have to have side over angle, sine of angle is equal to side over sine of angle. Or if we choose to find an unknown angle measure and put our sine of angle on top, then on the other side of the fraction, other side of the equation, we must have sine of angle on top. So that has to match. All right, so what can we do? Well, we'll go ahead and fill in what we know. We know that big B was 85 degrees, so B is to sine of 85 degrees, just like C was 3.9 inches, is to sine of angle C. And angle C was 34, so sine of 34 degrees. Everybody see it? We've completed our opposite side angle pairing. We filled up that fraction, C over sine of C. We have a single variable, B. We can solve for that in one step. What would you do to both sides to solve for B in one step? Hannah? Both sides by? Absolutely. Thank you. We're going to multiply both sides by the sine of 85 degrees, and that will solve for B in one step. Thank you. So, I know that B, I've gotten it by itself, is given by exactly 3.9 times the sine of 85 degrees, close angle, all over sine of 34 degrees, close angle. You could put 3.9 divided by sine of 34 degrees, close angle, and then times sine of 85 degrees. Both of those are equivalent. Let's go ahead and see what our approximation is then. So I'm going to go ahead and do 3.9. First, I'm going to do it the way that we wrote in red. That is divided by sine. Oh, I'm going to clear that out first, so we're ready to go with the new slide. I'm going to do 3.9 times sine of 85, close angle. Make sure you close your angle input before pressing divided by sine of 34 degrees. And I'm going to do it the way in red as well. If we had just done 3.9 and then divided by sine of 34 degrees first, and then multiplied by sine of 85 degrees last, we should get exactly the same thing. Do we? Yes, we do. Math works. So it looks like we get about 6.95. So about 6.95. And what label would we use on that 6.95? Right? What label would we use? Blake? Inches, it looks like. Inches? Good job. Well, that was pretty quick. What questions do you have about that first one? So the key was having that opposite side angle pairing. Let's consider another example. Number 2. In number 2, A equals 109 degrees, B is 31 meters, and angle C is 21. Let's go ahead and fill in our given stuff. So it looks like A is 109 degrees, so I know A is 109 degrees. I know side length B is 31 meters, so that's 31 meters. And side angle C, angle C is 21 degrees. In order to use law of sines, we need an opposite side angle parent. That is, both A's, both B's, or both C's. Right now, do I have both A's, both C's, or both B's, Jacob? No, I don't have an opposite side angle pairing complete right now, but could I get one? That is, with this given information, would I be able to pin down both A's, both B's, or both C's? Jacques?
Yes, because triangles have to add to 180, so you could just add 109.
Got you. And so we could get, anytime we have two angles in a triangle, regardless if it's a right triangle or otherwise, anytime we have two angles in a triangle, I get the third one for free because they must sum to 180. Good, Jock. So let's go ahead and do 180 minus 21 minus 109, and that equals angle B. So what's angle B? Looks like angle B in green is going to match side length B, and I'll have a complete opposite side angle pair. Then I can use law of sine. So angle B is going to be 180 minus 109 minus 21. Oh gosh, math is hard. That's 110, 130, so 50. You guys getting 50 degrees? Awesome. Now I have an opposite side angle pair. What am I looking for? I'm looking for side length A. So since I can use any form, I'm going to choose the form that has A on top, so I have less steps to solve. I'm going to use the circled A is to sine of A, just like it looks like we know both P's, so I'll use this equation. Let's do it. Unknown side length A is to the sine of angle A. Just like, and because we know both B's, I'll purposely choose to do B is to sine of angle B. Let's rewrite with our given information. A is my unknown, I don't know what that is, but I do know that angle A is 109 degrees. Oh yeah, equals side length B, 31 meters, over sine of angle B. We just found angle B was 50 cents. So we can now solve for side length A, again by multiplication, like Hannah said last time. We can solve for side length A by multiplying both sides, multiplying by the sine of 109. So it looks like side length A is given by exactly 31 over sine of 50 degrees times sine of 109 degrees, and that's approximately make sure you close your angle input, guys. Everybody try it. I'm going to do about 38.26. Everybody try it. Raise your hand if you got the same decimal. Were you able to reproduce that in your calculator? Good job, you guys. Good, good. So that's about 38.26. And the label on this one, 38.26, what would the label be this time? On?
It would be
Yep.
inches.
Is this one inches?
Oh, meters, sorry.
Meters? Awesome, thank you. So we've got about 38.26 meters. Great. Can we solve the following situation with law of sines? So let's go ahead and consider our given information. And you guys don't have a triangle this time, so you can just do a quick sketch of a non-right triangle. It doesn't have to be to scale, but we do want to consider what we know. So A is 30 degrees. I'll go ahead and fill that in. A is 30 degrees. That's red. C is 5 centimeters. So that's down here. Side length C is 5 centimeters. And B is 8 centimeters. So B is down here, that's 8 centimeters. So I've got red angle A known. I've got blue side length C known. I've got green side length B known. Do I have an opposite side angle pair known? No, we didn't last time, and yet we were still able to solve using law of sines, right? Because Jacques pointed out that my 180 degrees minus my two given angles equals the third angle, and then I had both B's. Can I use Jacques' strategy here? No, we only have one angle. We don't have two angles, and so can I pin down angle C? No. Can I pin down angle B? No. Do I have an opposite side angle pair? No, we do not have both B's, both A's, both C's, and we can't get them either. So, no, we can't use the law of sines. So we quit, throw it in the gutter, go buy another field trip to Wanna Bowl so we can throw back a few pictures of root beer. No, we're going to stay strong. We're going to tighten our belts, and we're going to charge ahead. We're going to use a new tool, and that tool is law of cosines. And so we've got law of sines, right? That's appropriate to use when we have an opposite side angle pair. When we don't have an opposite side angle pair, then we're going to use the law of cosines. We're not going to prove the law of cosines as in much detail as the law of sines. The law of sines went pretty quickly. The law of cosines is a little bit trickier, but we could still drop an altitude h from angle C. And then we utilize a combination of cosine, since it's law of cosines, and Pythagorean theorem with the right triangles we've created in order to generate the law of cosine. You're not going to have to do this on a test or quiz, but it's important to note that this isn't just coming from nothing, it's coming from things you already know. The Pythagorean theorem and cosine ratios for right triangle trade from yesterday. So you guys know where this comes from. It's not just magic, right? It's not math magic, it's based on things that you guys know and can produce. All right, so let's go ahead and take a look at our picture. We'll finish the following statements. X squared in the left triangle plus h squared in the left triangle equals a Pythagorean theorem. That would equal a squared, the hypotenuse length squared. At the same time, y squared in the little triangle plus h squared in the little triangle equals the hypotenuse in the little triangle squared is b squared. Side length C is given by the sum of left triangle x base plus right triangle y base, so C is x plus y. Cosine of angle A is a ratio adjacent over hypotenuse. What side length is adjacent angle A? Well, that's touching but not the hypotenuse, so that's y. Over hypotenuse is b. So, why? Well, because if we were to rearrange that top, a squared minus x squared equals h squared, and b squared minus y squared equals h squared, so we could again set those equal to each other. We could substitute in our given information, rearrange, substitute again, and voila! We get one form of the law of cosine. You won't have to do that on a test or quiz, but it's important to note that all of this just comes from our right triangle trig ratios, Pythagorean theorem, and substitution. Okay? Let's go ahead and see the different ways law of cosines can be rewritten. Just like law of sines can be rewritten, right? Several different ways depending upon what given information we had and what we wanted to find. So too can law of cosines be rewritten in several different forms. The key is recognizing that opposite side angle pair again drives the problem in terms of the formula. This a squared, if it's the one isolated, that alone by itself on one side of the equal sign, then that must match angle A. But there's nothing special about opposite side angle pair A. It could have been rearranged for opposite side angle pair B. In this case, b squared would be given by the sum of the squares of the other two sides. That would be a squared plus c squared minus 2 times a times c times the cosine of angle B would be my opposite side angle pair that match, right? That are my bookends here in the law of cosines. And there's nothing special about my b's, right? I could have had side length C and cosine of angle C as my bookends on the law of cosines. Let's everybody write these three forms then. So there's nothing special about the letters A, B, and C. What's important is about the placement. And so we need whatever side length is isolated on one side squared, that has to be opposite the cosine of that same angle. The other two sides, right, whichever one you didn't use, they go here and here. So if I chose to solve for c squared, then I have what here? Well, I have the other two. A squared plus B squared. And then minus 2 times A times B times cosine of angle C. And so the opposite side angle pair again drives the party, whether we're law of sines or law of cosines. If I have an opposite side angle pair known, then I use law of sines. If I don't have an opposite side angle pair known, then I use law of cosines. Awesome. Let's go ahead and take a look then how this will help us solve. All right, so let's go ahead and fill in our A is 30 degrees. This is the picture you already had, right? This is the same thing that you already had. C is 5 centimeters. And B equals 8 centimeters. Do I have an opposite side angle pair? No. Can I use law of sines? No. But I can use my new tool, law of cosines, so long as I set up the equation that has the opposite side angle pair. Which angle do I know something about? A, B, or C? Chrissy? Which angle do I know? I know angle A. I know angle A, right? If I know angle A, then I'm going to use the law of cosines that includes angle A. And only one of them included that. That was my first one. So I'm going to use this one because I know angle A, and this tells me information about the side length that's opposite it. Let's go ahead and see what we can do here then. So I'm going to start out with the A form of cosine, law of cosines, because I know information about angle A. I know that A squared is given by the sum of the squares of the other side, b squared plus c squared minus 2 times b times c times the cosine of angle A. Let's fill in what we know. We know b is 8. So I just fill in 8 and then squared. Plus we know c is 5. So we just fill in 5 squared minus 2 times, and we know that b is 8 still, and c is 5 still, and the cosine of something, we know angle A is 30 degrees. Do you guys see we knew this whole right side of the equation? We can plug in a variable value for everything in there. And now all we have to do is solve for angle A. I'm sorry, side length A. Right now I have A squared alone. I want to get A alone. So what undoes squaring to solve for A? Right? What undoes squaring? Ian? Square rooting. And so while in general, I take the positive and negative square root when undoing a squaring, I can purposely ignore the negative because we're trying to find a side length in centimeters, and we can't have a negative centimeter length, right? And so we'll go ahead and just take the positive square root for my answer, although I'll still list it because I don't want to, again, have trouble falling asleep at night and be like, oh, technically we're supposed to take the positive and negative square root. And what is it? It's the square root of 8 squared plus 5 squared minus 2 times 8 times 5 times the cosine of angle 30 degrees. All right. So I'm not going to do intermediate evaluations. I'm going to go to my calculator and do that one time. So I'm going to do that one time. You can do it however you're comfortable, but you have to produce it on your own on the test. So I'm going to do 8 squared plus 5 squared minus 2 times 8 times 5 times cosine of 30 degrees, close angle, close radical. Pinch of salt all over the shoulder. Voila! I'm getting a side length that's about 4.44 centimeters. Does that seem reasonable? Well, I had 5, I had 8, so 4.44 seems in line, right? It's not something like the 13,062 that we got the other day. So the reasonableness of the answer, so we'll say about 4.44 centimeters. Did I get everybody clicked in there? We're good? 8 squared plus 5 squared minus 2 times 8 times 5 times 7. Hey, awesome. What questions do you have about this first one? So that was the one we had already investigated before. Now let's go ahead and take a look at a couple more. So let's take a look at this triangle. as I consider the given information, I'm looking for an opposite side angle pair, right? Do I know an opposite side angle pair? Well, I see that D is opposite 71 degrees, but do I know what D is? No, I'm trying to find it. And so yet again, I've got a situation where I do not have given information about an opposite side angle pair, nor can I find an opposite side angle pair by doing our 180 minus strategy. So this is a situation not for law of cosine, I'm sorry, not for law of sines, but for law of cosines. I don't have an A, a B, or a C though. So is it back to wannable? No, remember these forms? Doesn't matter what letters are used, what matters is my opposite side angle pairing. So if my situation includes a side length D, right, then my angle opposite D is going to be my cosine of angle 71. So we can use whatever letters we want, so long as the opposite side angle pairing is at the start and end of my law of cosines. In this case, D squared, right, equals the other two side lengths squared. So that would be 16.8 squared plus 21.4 squared minus 2 times 16.8 times 21.4 times the cosine of 71 degrees. What do I want to solve for? I want to solve for D. What undoes squaring? Square rooting. So D will give it by the square root of 16.8 squared plus 21.4 squared minus 2 times 16.8 times 21.4 times cosine of 71 degrees. Let's try it. See if we can't generate the same thing. Everybody, please try it. So we're good. Second square root. Oh my goodness gracious. 16.8 squared. I'm getting carpal tunnel just thinking about entering this data. Squared. What's that? Lag? Too fast? Too furious? Hey, that reminds me of a movie. Too fast, too furious. Bless you. Did I double click anything? Are you guys okay? Let's see if we get the same one. Raise your hand if you had 22.50, 22.50. Yes! That's great news. So about 22.5. No units? No units. So I'll just leave it at about 22.50. Great. Okay. The next one asks me to find not an unknown side length, but an unknown angle. And so up until now, we've been finding side lengths using law of sines and law of cosine. In this case, we're asked to find an unknown angle measure. Okay, an unknown angle measure. And so we know that we get to use our inverse trig functions when we find inverse angles. It's just that we don't know if we should use law of sines or law of cosines. So, do we know a complete opposite side angle pair right now? Taylor? No, we don't. We're asked to find angle E, which is opposite side length 9, but we don't know what it is, right? So we don't have a complete side angle pair. We can't fill up a fraction in law of sines. So what are we going to use? We use law of cosines. And it doesn't matter if we have A, B, or C. In this case, we have E. What matters is that the cosine of the angle is opposite that isolated side length squared. So what would I start out with my law of cosines form? I'd start out with, not with 5 squared, not with 8 squared. I'd start out with 9 squared because it's opposite of the angle E that I'm trying to find. So we'll go ahead and start out. I get 9 squared equals the sum of the squares of the other sides, 5 squared plus 8 squared minus 2 times 5 times 8 times the cosine of angle E. Oh gosh. What am I trying to solve for? I'm trying to solve for angle E, and so I've got a lot of stuff to do in between now and getting E by itself. I prefer to do this in one entry in my calculator, that way I'm less likely to mess stuff up or carry over my answer in order of operations. However, many of you will like to evaluate this first, and the choice is yours. I just want to make sure that you're not making a mistake. So I'm going to go ahead and subtract over my 5 squared, my 8 squared. Then I'm going to go ahead and divide. I'm going to divide both sides by the opposite of 2 times 5 times 8. And I'm just going to do this once to show how I'm getting my entry each time. That isolates the cosine of angle E on one side. So this gets the cosine of angle E alone on one side. And I get 9 squared minus 5 squared minus 8 squared all over the opposite of 2 times 5 times 8. Now, that's all well and dandy. But I want to find the measure of angle E. And right now, do I have angle E alone? No, I have the cosine of angle E alone. So what operation undoes cosine? What am I going to do to solve for E? Caitlin?
Inverse cosine.
Inverse cosine, absolutely. If cosine of E equals blah, then E equals the inverse cosine of blah. And that's true whenever we're trying to find an unknown angle. We'll use our inverse trig function. It's just that on top I have this quantity 9 squared minus 5 squared minus 8 squared all over. And on bottom I have this quantity negative 2 times 5 times 8. All right, so what's with the colors, Mr. Fritz? Well, I'm trying to show that's the parentheses I'm going to be entering to separate my numerator and denominator. Now, you could have simplified and evaluated along the way. That's fine. I just don't want you to make a mistake with your order of operations and your enter or your second answer. So I'm going to do a single line entry. I'm going to do one entry here. I'm going to do the inverse cosine of, and I'm going to open up my numerator. My numerator is 9 squared minus 5 squared minus 8 squared. And I'm going to close my numerator. Flag. Flag. Bless you. Close numerator. Divide by open denominator. Opposite of 2 times 5 times 8. Every year, students make a mistake on the find the missing angle using law of cosines question on the test and the quiz, and they lose points here. So I want everybody to make sure you can generate the correct angle measure here. You shouldn't get an error. Right? Many of you are going to get an error. We don't want to get an error. We're going to close our inverse cosine now. Does everything match? 9 minus square root of 5, and voila, about 84.26 degrees. So by using these parentheses and the color coding, I've made sure that I haven't made a mistake entering it. Make sure you can do the same. That was pretty sweet. What questions do you guys have on number 2? All right, let's go ahead and take a look at our cool clip art. Gosh, I love clip art. I don't know where to put this though. So it's hard to overstate the importance of trigonometry in our daily lives, right? We tend to go about our lives using our phones, right? Walking through the hallway, trying not to run into walls or other people, right? And all the GPS features on our phone are based on trigonometry and the concept called triangulation. So it's hard to overstate how important trigonometry is for us in terms of global positioning systems on our car, right? When we're going to the call center, we just enter the address or give a speech to text, and then it takes us there, right? And how does it do it? Well, it does it with GPS systems and trigonometry. So it's pretty cool. All right, let's go ahead and complete our closure then. So when is it appropriate to use Sohcahtoa? Please don't say it out loud. Just write down when is it appropriate to use Sohcahtoa. Think about what information we need. What other methods do we have for solving for missing parts of triangles? When should we use law of sines versus to solve for missing sides or angles in a triangle? And then when must we use law of cosines to solve for missing sides or angles in a triangle? Go ahead and put a written response for each, and then I'll call on you to share. Okay, ladies and gentlemen, thank you. We've gone back to our example, our first law of cosines example. We're going to find all of the missing sides and angles. We only found side length A. Well, that's good news. We have side length A, side length B, side length C. And so now all we have to do is find the remaining two pieces. What? Well, we still have to find angle C and angle B. Right? We still have to find side angle C and angle B. So I'm going to go ahead and set up an equation that will allow us to find our missing angles. It looks to me like I could use law of sines. Now that I have a complete opposite side angle pairing, I know both A's. Right? I know both A's. And so I'm going to go ahead and set up a law of sines equation where one of my fraction is my A, side length A and sine of angle A information. I'm first going to find angle C. And so because my unknown is an angle, I'm going to start out with not a side length on top. I'm going to start out with sine of angle C on top. Sine of angle C is to side length C, just like sine of angle A is to side length A. Right, see? We're going to go ahead and find angle C. I'm going to put now my sine of angle C on top because that's my unknown. And I know both A's. Therefore, I'm choosing the sine of angle A over side length A to complete my equation. Now we'll go ahead and plug in our given information. Sine of angle C we don't know, but we do know side length C, and that's 5. We know angle A is 30 degrees. We found side length A to be 4.44. Now, we can solve for sine of C by multiplying both sides by 5. So we're going to times by 5 to isolate our sine. That gives us sine of angle C is equal to 5 sine of 30 degrees all over 4.44. Everybody take a look. We're so close. We've used law of sines to generate an equation that has my unknown angle C in it. We've isolated the sine of angle C through multiplication, and now we just have to get angle C by itself. Well, what function undoes the sine function? How am I going to solve for the measure of angle C? Samantha? Absolutely. We'll do the inverse sine of both sides. If sine of angle C equals blah, then angle C equals the inverse sine of blah. In this case, blah is 5 sine of 30 degrees, close angle, all over 4.44. So on my grapher, I'll get an approximation for that. I'll do the inverse sine of numerator 5 sine 30 degrees, close angle, over, and it was 4.44 0.49181. I'm getting about 34.27 degrees. I'm getting about 34.27 degrees. Hey, that's good. So, do I have to use law of sines or law of cosines to find my final angle? Neither, right? We can use Jacques' strategy to find my remaining angle. What would I do for that, Hans?
You would turn the angles A and C first, and you would subtract 1.
Absolutely. We can do our 180 minus to get that third and final angle B for free. So I'll do 180 minus 30 minus the 34.27 that we just found. Numbers are hard, but our calculator makes it easy. 180 minus 30 minus 34.27. Looks like angle B is about 115.73. Gosh darn it, we solved all of it now. So 115.73 degrees. Thank you for your patience and for returning to that example so that we could practice doing an inverse trig function with law of sine. Back to the closure. Written response for each, and then I'll call on you to share with the class. Okay, ladies and gentlemen, go ahead and share with the class. When is it appropriate to use Sohcahtoa, right? When is it appropriate to use Sohcahtoa? Kendall?
When dealing with the right triangle.
Good, thank you. When we're dealing with a right triangle, then we're authorized to use our sine, cosine, and tangent trig ratios. So we need a right triangle in order to use Sohcahtoa. What other methods do we have to find missing sides or angles? Right? What other methods do we have? Mark?
Law of sines.
Good. We've got our law of sines, and we've got our law of cosines, each of which we generated and used today. Thank you. When is it appropriate to use law of sines? So what do we need to use law of sines? What must we have for given information? Joe?
You have the opposite side angle there.
Good. We need both A's, both B's, or both C's. So we need an opposite side angle pair, known information. Or be able to find it. So we need an opposite side angle pairing. Which means that we use law of cosines if we don't have an opposite side angle pair. Okay, ladies and gentlemen, as we work through our trigonometric applications starting tomorrow, it's going to be important that you're able to determine which tool is appropriate to use. So everybody take a look at our flow chart to close out our discussion today. Typically, when asked to find a missing side or missing angle, we start at the top of our flow chart and first look and see if we have a right angle. If we have a right angle, then we have a right triangle, then we're authorized the use of all of that special right triangles, Pythagorean theorem, and Sohcahtoa. And so, for our left branch, we label, is it a right triangle? If yes, then we can use special right triangles, Pythagorean theorem, or Sohcahtoa. Pythagorean theorem, we know, is what, Jacob?
A squared plus B squared C squared.
The sine is ratio of opposite over hypotenuse, so I'll go ahead and say opposite over hypotenuse. Cosine is the ratio of adjacent over hypotenuse. Tangent is the ratio of opposite over hypotenuse. If I don't have a right triangle, then I'll go ahead and see, do I have an opposite side angle pairing, right? Do I have both C's? Do I have both B's? Do I have both A's? If so, then I can use the law of sines, where I need an opposite side angle pairing to fill up the fraction. If no, then I'll have to use the law of cosines, which is a little bit more complicated, right? But still, we use to find missing sides and missing angles in class today. This flow chart you'll see again, right? And you want to be using it as you attack these missing side, missing angle problems in our application packets next time, day 3. What questions do you guys have on our discussion? there's a completed chart and your assignment. Nice job. I'm going to go ahead and stop the recording and upload it to our YouTube channel.